So let's go back to the standard poverty of stimulus argument. One way to conceive the acquisition process is as follows. The child is trying, unconsciously of course, to come up with an internal grammar that will account for the sentences heard in the PLD. That is, the child is trying to construct a set of rules that will generate the sentences in the ambient language. In this sense, the child's situation is analogous to a scientist trying to formulate and choose hypotheses that will account for the observed data. Now, at this point, the child faces its first hurdle, namely that hypothesis choice is always underdetermined by data. What this means is that any finite body of data will always be consistent with more than one hypothesis, and in fact with an indefinite number of them. This illustrates the general phenomenon of the underdetermination of theory by evidence, which is a view mostly associated with the French physicist Pierre Duhem and the American philosopher W.V. Quine. To visualize this, imagine that you have a very special pet named Grok, who eats a lot and has a very strange metabolism. You want to know, in the case of Grok, what the relation is between the amount of food ingested and the weight gained. Thus, on a series of days, you feed it different amounts of food, measured in kilograms, and at the end of the day, you measure how much weight it gained in terms of grams. Then you plot the results in a chart that indicates how much weight Grok gained for the different amounts of food. So when you fed it half a kilo, it gained 1 gram. When you fed it 2 kilos, it gained 2 grams. When you fed it 3 kilos, it gained 4.5 grams. And when you fed it 5 kilos, it gained 6 grams. So you have this data, but now you want to hypothesize the shape of the relationship between the two variables. One possibility that comes to your mind is that it is basically linear, and that the number of grams gained is always proportional and indeed identical to the number of kilos fed. Sure, most of the measurements actually fall outside your line, but you can explain that away by assuming that it is due to measurement error, since you can only expect so much accuracy from a scale that you bought at the dollar store. But there are other possibilities. It may be that what your data are pointing at is an S-shaped relation, like the one pictured here. According to this function, if you feed Grok less than 2 kilos, it will gain a little less than 1.5 grams. But if you feed it 2 kilos or more, then there will be a quantitative leap, and it will gain a little bit over 5 grams. Another possibility is a smooth curve like the following that sticks pretty close to your data points. Yet another one is this crazy curve that your little brother drew, thinking that your notebook was a connect the dots book. Which, in a way, you were, and you realize that there is an infinite number of ways of tracing a curve through the observed data points. And this isn't just because you had 4 observations. Even if you increase the number of data points, you will still have that problem in principle. For the child acquiring language, the underdetermination problem means that the PLD will always be consistent with an indefinite number of hypothetical grammars. Hence the first premise of Lawrence and Margolis' statement of the poverty of stimulus argument, namely that an indefinite number of alternative sets of principles, that is, grammars, are consistent with the regularities available in the primary linguistic data. For an example, imagine a child acquiring the rule to formulate yes-no questions in English. Suppose that the available input at some point consists in declarative sentences paired with their corresponding interrogatives. One such pair could be 1 and 2. The man is tall and is the man tall? Which rule can take us from a sentence like 1 to its corresponding question, as in 2? Well, it could be hypothesis 1. Move the third word to the front of the sentence. That would do the job. But it could also be accounted for by hypothesis 2. Move the first occurrence of is to the front of the sentence. Or by 3. Move the first occurrence of an auxiliary to the front of the sentence. Or by 4. Move the auxiliary immediately after the sentence's subject to the front of the sentence. In fact, the number of fitting rules is open-ended, given all the parameters that could be involved. For instance, you could have something like move the third word to the front of the sentence only if the sentence is singular. So what is the child to do? Well, the child would be in the same situation as any scientist. So, although it is acknowledged that as a matter of logic, the underdetermination is not completely eliminable, Nonetheless, when faced with a choice between two or more hypotheses that fit the data equally well, there are at least two kinds of strategies that we can follow. For instance, we can apply constraints of hypotheses, such as simplicity, elegance, and naturalness. In this way, we could choose the simplest hypothesis or disregard those that we deem unnecessarily complex. Or we could prefer those that seem to us more natural or more likely, given other things that we assume about our subject matter. So let's go back to our Grok example. Simplicity, in some pre-theoretical, non-technical sense, might lead you to prefer a perfectly linear relation, as in 1, or a sort of a two-value outcome relation, as in 2. Likewise, you might think that 3 is overfitting the data, is hugging the data too closely, and it won't generalize beyond the observations. And 4 is too weird and too unnatural to be considered a viable candidate. So in this way, we can rule out, or at least rank, the hypothesis. The other strategy would typically be pursued in tandem with the previous one is to gather more data that is relevant for deciding between hypotheses. Again, back to our example. Suppose that we want to choose between hypotheses 1 and 2. To do so, we gather more data. Which particular observation would be most relevant for deciding between the two hypotheses? Well, we know that they make different predictions for the case in which we feed Grok 2.5 kilos. Hypothesis 1 predicts that the weight gain will be 2.5 grams, whereas 3 predicts that it will be 5. So one reasonable thing to do would be to feed Grok 2.5 kilos of food and see how many grams he gains. That would help us decide between those two choices. So the two strategies we have mentioned, namely applying constraints on hypotheses and gathering relevant evidence, are open to any inductive learner, that is, any learner that is attempting to make a potentially risky inference from the data. In this family of general-purpose strategies, we can also find related inductive processes like generalization and analogy. This would also be open to any learner, such as the empiricist learner. So suppose our empiricist learner is acquiring English. Well, in this case, such a learner would be in trouble, according to Lawrence and Margolis, as their second premise states the correct set of principles, that is, the correct grammar in quotation marks, needn't be, and typically isn't, in any pre-theoretical sense, simpler or more natural than the alternatives. This can also be exemplified with our previous example of the polar interrogatives. Suppose that we're trying to come up with a rule that derives yes-no questions from their declarative counterparts, as in sentences 1 and 2. One possible hypothesis, which we could call Rule 1, involves taking the sentence simply to be a string of words and relying on the property of linear order. It would say, search left to right until you reach the first occurrence of the word is. Then transpose this occurrence of is to the beginning of the sentence, that is, to the left. Here, 1a and 1b illustrate the input and output of the operation, respectively, and you can see that there is a gap in 1b in the place where is was extracted. This rule is pretty straightforward, but is it correct? What happens when we apply it to a sentence such as 3? The man who is in the park is tall. Well, the analyzer would crawl left to right, then find the first occurrence of is, and then it would move it to the left edge of the string. And the outcome would be, is the man who in the park tall? But this is definitely not the question that corresponds to 3, and in fact isn't even an acceptable English sentence, a fact that linguists mark by putting an asterisk in front of the offending string, though I would personally prefer a yuck symbol. In parentheses, this is a mistake that children seldom, if ever, make. So suppose that we have this other hypothesis. First, it requires us to analyze the sentence, not merely as a string of words, but as a hierarchical structure composed of phrases. Then we locate the first auxiliary is after the subject-noun phrase, which in this case would be the auxiliary of the main clause. And finally, we would transpose this occurrence of is to the beginning of the sentence. This would be a very rough example. Here we have divided the sentence between a subject and a predicate, both phrases. These aren't really the labels or the analysis that generative linguists use, but let's keep these notions that may be familiar to us. What is important is that we not only have linear order, but also relations of constituency, which form a hierarchy. So we have added an extra vertical dimension to our analysis, so to speak. So the rule tells us to locate the auxiliary of the main clause, which in English occurs after the subject phrase, and then move it to the front. The rule also applies to our previous example, of course. We find the main auxiliary after the subject phrase and move it to the front. And the same applies if we have a more complex subject phrase. And indeed, it applies no matter how long or complex the sentence gets, as long as we are focusing on the relationships among phrases and not on the linear positions that the component words happen to occupy in a specific sentence. So here we have these two competing hypotheses. Hypothesis 1, from a pre-theoretical perspective, seems simpler and easier to compute, since it only involves regarding the sentence as a string of words, where only linear order matters and counting is the relevant operation. However, hypothesis 2 is closer to how language actually works. I'm not going to say that it's correct, of course, but it's close to the vicinity of the ballpark of correctness. Now, 2 also seems more complex or less intuitive, since it requires adding, alongside linear order, a vertical dimension of hierarchical analysis as well, and also the introduction of the notion of a phrase and a host of new entities and relations such as constituency and the like. And what about other items in the toolkit of the inductive learner, such as analogy and generalization? Well, analogy has sometimes been mentioned as a key process in learning language. Nevertheless, consider this example. The predicate eat can appear with an object, as in 5. John ate an apple. Or we can delete the object. This is because eat can also appear without an object, as in John ate. When eat doesn't have an overt object, it means that the reference of what is being eaten is indeterminate. So 6 means John ate something or other. Now suppose that after looking at 5 and 6, we encounter 7. John is too stubborn to talk to Bill. On the basis of pairs like 5 and 6, it could be inferred by analogy that whenever a verb takes an object and then the object is missing, the now implicit object is taken to be arbitrary in its reference. So what happens when we delete the object Bill from 7? And we get John is too stubborn to talk to. 8 means John is so stubborn that some arbitrary person won't talk to him, that is, John. So the missing object refers to John. Crucially, it does not mean John is too stubborn to talk to someone or other, as you would expect from the previous analogy. So the analogy from eat to talk to fails. And this is not an isolated case. Language is full of pitfalls for the analogy-based learner. That was about constraints on hypothesis. But remember the other strategy, gathering more evidence. So what about getting more data? Well, the problem is not as straightforward as it seems at first. To begin with, the child has to identify what stimuli count as data and which do not. One component task here would be to identify the basic sound units of language, in the case in which the child is acquiring a spoken language. Here, the learner needs to distinguish linguistic input from non-linguistic one. So it must separate linguistic vocal noises from non-linguistic ones, such as coughs, gurgles, etc. And it must distinguish relevant from irrelevant variations, such as in timbre, speed, and the like. Moreover, if the child is going to establish morphemes and words as units of analysis, it needs first to establish boundaries in speech signal. But this isn't trivial either. This figure shows a waveform of the recorded utterance, "The spotted cat skidded by." The horizontal axis shows time, and the vertical axis shows the loudness of the signal at each point. When the signal is at its widest, that means greater amplitude, and therefore that the voice was at its loudest. And where the waveform is basically just a horizontal line, the speaker was silent. But because of background noise, there is never perfect silence, of course. Now, based on this information, try to figure out where each word of the sentence begins and ends. Okay, you have this other figure. So this second figure shows the waveform along with the locations in time where the words occur, approximately. And, the approximate word boundaries are indicated by the pound symbol. You're probably tempted to place your word boundaries wherever there was a silence. However, notice that there isn't necessarily a silence between words. Also, notice that sometimes there is a silence inside a word. And this can be seen where the utterance contains sounds like P, T, and K. So in the words spotted and skidded, there is an S before a consonant in the same word. Yet the waveform shows that there is silence between the two sounds. On the other hand, there is no silence between the words the and spotted. This situation is typical, and if we presented you with a recorded speech from an unfamiliar language, you wouldn't be able to find word boundaries by either looking at the waveform or listening to the recordings. So, how does the empiricist learner manage then to find the word boundaries in the continuous stream of speech? Moreover, the learner needs to normalize sounds over different sounds and different contexts. This is because phonemes can be manifested in different ways in different contexts. So compare the P sound in pit and spit. The first consonant of pit has an extra puff of air after it, right? Which is not found after the P of spit. And linguists describe this by a diacritic of aspiration, the superscript H. So if you put your hand in front of your mouth when you're saying pit, right, you notice that there's a little puff of air, but when you say spit, it's not as noticeable. Now, even if word boundaries are set and normalization has been achieved, the surface of language is rife with ambiguous phonological and lexical variation that must be disentangled. So, for instance, these three words sound the same in American English. Moreover, to has two meanings, one corresponding approximately to excessively and the other to as well.